Today, we continue our discussion of spherical harmonics that carry the angular variables of the wave function. Let's see where we stand in solving the eigenfunction problems of the three commuting operators h, L2, and L3. For an introduction to these problems, refer to Lecture 8 of this series. In the last lecture, we have found the eigenvalues for L2. In a moment, we shall look at its eigenfunctions. For now, we move on to an even easier problem, solving for the eigenvalues and eigenfunctions of L3. As for the energy eigenfunctions, we shall deal with them a bit later, when we move on to specific applications like the hydrogen atom and harmonic oscillator. Let's solve this equation and demonstrate why the eigenvalues are in integer units of h bar. Going to position space, the representation of L3 is given in a green box as we have derived earlier. This gives the following first-order differential equation. Recall that the eigenfunction psi is separable into the radial and angular variables. This means the radial part of psi can be factored out in this angular equation. This equation says that the spherical harmonics y is also the eigenfunction of L3. Solving this will give us the dependence of y on the angle phi. The proportionality factor of this solution can only be a function of the angle theta. Since going around the z-axis in a full circle will bring us back to the same point, if we require the wave function to be a single value function in position space, then the period in the angle phi must be 2 pi. This implies that m must be an integer, which could be positive or negative. Thus, we have just solved the eigenfunction equation for L3. Although we shall soon find out that its eigenvalues need to be constrained further for a fixed value of L. At this stage, we could plug the spherical harmonics y, now left with the unknown function f, back into the eigenfunction equation of L2, then solve for f theta. Note that since y is defined by the two eigenvalues L and m, let's label it this way. Similarly, we can denote the function f by plm to reflect these eigenvalues. These functions are known as the associated Legendre functions, but more about them later. The notations carry forward to the joint eigenfunction psi of the three operators h, L2, and L3. This is where we stand in our search for eigenfunctions. Even now, without actually solving the differential equation of L2, we can still figure out more properties of the spherical harmonics y. We do so with the help of more clever arguments. Recall the Cartesian coordinates that describe the position vector. Each coordinate is linear in R, and if they are factored out, we have the components of the unit vector x hat. We claim that the spherical harmonics ylm is a homogeneous polynomial of degree L in terms of these components. That is, the sum of powers of each term in a polynomial of these components must sum to L. Let's prove this now. We start with the full shared wave function psi. Once again, it would be instructive to examine this in the region where R approaches 0. As explained earlier, the term that would dominate in this region in the expansion of the radial function would be the lowest power in R, L is just the value of this power. Let's look at an equivalent power series expansion of psi in Cartesian coordinates. In the limit of r approaches 0, the sum of the powers of these coordinates must be equal to L to be consistent with the expression in radial coordinates on the right-hand side. RL can therefore be factored out of this equation. This means the spherical harmonics YLM is a homogeneous polynomial of degree L. For an example of the terms that could be in a homogeneous polynomial, take the case where L equals 2, and the allowable terms will be the following. These are just all the possible combinations with positive powers that sum to L. We have mentioned earlier that for a fixed L, the values of M are constrained for the spherical harmonics YLM. Let's now derive a relation between these two eigenvalues. For this purpose, it is convenient to define the following coordinates, x plus and x minus. They are both linear in R, and therefore do not change the way we count the powers of R in the previous discussions on homogeneous polynomials. Together with x3, they are in fact equivalent to the original Cartesian coordinates. This can be written in the following form, in which the relation to the eigenfunctions of L3 is made explicit. It is clear that the value of M must put a constraint on the powers of x plus and x minus within the spherical harmonics. x3 is not constrained because it is independent of the angle phi. Let's look at the full eigenfunction in the region where r approaches 0. A typical term in psi consists of the following powers of coordinates, where the powers sum to L. Each individual power is positive because they are part of a power series. Psi is a homogeneous polynomial of degree L. The term consisting of the product of x plus and x minus corresponds to the eigenfunction of L3. This implies that M must be equal to the power of x plus minus that of x minus. These three conditions define the relation between M and L. The second and third condition lead to the following condition on nu plus and minus. This means the magnitude of their difference must be less than L. Applying this to the first condition implies, which says that M is an integer between L and minus L. Thus we have derived the constraint of L on M. M is also known as the magnetic quantum number because it describes the differences in the energies of an atom in an external magnetic field. Counting the number of values for M, we get this is the number of eigenstates of L3 associated with the quantum number L. Thus we now have the complete solutions of the eigenvalues of both L square and L3. All that is left now is to solve for the remaining unknown function within the spherical harmonics. An important question to ask would be, is it actually possible to completely determine the function y just from the remaining equation of L square? This is a question of counting the number of constraints versus the number of variables and see if they match up. To do the counting, it will be convenient for us to rewrite this equation into a different form. Recall that we have earlier derived the following relation between L squared and the Laplacian operator. Let's apply this to the function RL times YLM. This is a homogeneous polynomial of degree L in Cartesian coordinates. Looking at the second term on the right-hand side, all the R dependence of this term is in the green box. This is just a couple of simple derivatives which we have previously calculated. Applying the equation in the yellow box, the operator L squared on the left-hand side can be replaced by its eigenvalue. Notice that this is equal to the last term on the other side of this equation, and therefore cancels. Dropping the factor in the red box, we end up with the Laplace equation. This has the generic form where the function f in our case is RL times YLM. So this Laplace equation is actually equivalent to the eigenfunction equation of L squared. We shall see that this is more convenient for counting constraints. Recall the recent result which says that the number of distinct values of m for a fixed L is given by 2L plus 1. This means we must expect this number of independent solutions to the Laplace equation. More precisely, all possible linear combinations of y with the allowable values of m must satisfy the Laplace equation. The degrees of freedom that quantify all the possible solutions are given by the constant coefficients c. 2L plus 1 is therefore the number of unfixed constants. If we further specify the value of m, then the solution to the Laplace equation would then be pinned down uniquely. Thus, the key objective of our counting would be to show that the Laplace equation could provide sufficient constraints to narrow down the degrees of freedom of the function y down to 2L plus 1. So to begin, we first remove the parameter m from the notation of y, because this parameter is not fixed. Our only assumption initially is that RL times y must be a homogeneous polynomial of degree L. The Laplacian operator, due to the fact that it's a second derivative, would thus reduce the degree by 2. So the left-hand side of the Laplace equation is a homogeneous polynomial of degree L minus 2. Try to keep this in mind, as this will be important in a minute. Let's count the number of degrees of freedom in YL. By this we mean the number of independent coefficients in a homogeneous polynomial of degree L. This means we have to sum over nu1, nu2, and nu3, while keeping the constraint in the blue box. This implies that for a fixed nu1, nu2 is related to nu3 like so. So the index nu3 may be eliminated in favor of 2. The maximum of nu2 in the sum corresponds to nu3 equals 0, and the minimum to nu3 equals L. By the relation in the green box, the sum in the yellow box is just the total number of terms in the sum. The sum in the green box can be solved by the famous trick used by Gauss as a schoolboy. Thus we have the total number of degrees of freedom in the function yl. This is the number of distinct coefficients a in this polynomial. yl is the initial function not yet subjected to the constraints of the Laplace equation. We now demand that it satisfies the Laplace equation. Recall that the second derivative means the left-hand side of this equation is a homogeneous polynomial of degree L-2. Thus the Laplace equation gives the following polynomial equation. The f's are the coefficients of this polynomial, and they are functions of a, the coefficients of yl. Now we count the number of constraint equations in the red box. This is the number of distinct coefficients f in a homogeneous polynomial of degree L-2. But we already have the solution above for the case of general degree L. Therefore, the number of degrees of freedom in the function yl, after satisfying the Laplace equation, is just the number of parameters minus the number of constraints. And we have shown that the number of degrees of freedom of yl is exactly equal to the number of allowable values of m when L is fixed. Thus, if m is specified, this is sufficient to give a unique solution to the Laplace equation, which is the spherical harmonics ylm. A few examples should make this clear. We shall calculate the first few spherical harmonics, starting with the assumptions that they are homogeneous polynomials of degree L, and that they must be proportional to the eigenfunctions of L3 with the specified m. Then applying the Laplace equation will be sufficient for us to obtain the spherical harmonics. Let's start with L equals 0. The only possible m is 0. Thus this spherical harmonics is simply a constant. This is both a homogeneous polynomial of degree 0 and the eigenfunction of L3 with m equals 0. Of course, this satisfies the Laplace equation in an obvious way. Thus y00 is just a constant, which can be fixed by the normalization condition of the wave function. The next example is less trivial, L equals 1. This allows the following values of m. For the case of m equals 0, r times y10 can take the general form of this polynomial of degree 1. The requirement that this be proportional to the eigenfunction of L3 associated with m equals 0, which is independent of the angle phi, implies that only the x3 component is allowed, since both x plus and x minus depends on phi. Once again, the Laplace equation is trivially satisfied since we are taking a second derivative on a function first order in coordinates. Indeed, we need not worry about the Laplace equation at all for the family of spherical harmonics with L equals 1 due to this reason. Factoring out R, we have the spherical harmonics y10 proportional to x3 hat. This is the solution for L1 M0. What about when m equals plus or minus 1? We can solve them together. The requirements on M tell us that this has to be proportional to x plus minus. Next, we move on to the family of functions with L equals 2. This will provide us with the first example where the Laplace equation actively constrains the solutions. Let's start with the easiest case and proceed to the more complicated. This is the case for m equals plus minus 2. This condition, together with L equals 2, leaves only one possibility, which has to be x plus minus hat to the power of 2. There's no room for x stray because it increases L by 1 without contributing to m, but we need the maximum allowable value of m equals plus minus 2. Also, negative powers of coordinates are not allowed, as these are not present in a power series, so there's only one solution to these constraints. Let's check if this satisfies the Laplace equation. This last term is 0 under the derivatives. The remaining two terms cancels each other. Thus this satisfies the Laplace equation. Therefore this is the solution y2 plus minus 2. Moving on to m equals plus minus 1. Based solely on the values of m, y must be proportional to the wave function. At this point, we could make the following guesses. For m equals 1, could we have two factors of x plus and one factor of x minus, and for m equals minus 1, just the other way round? Turns out that these are not acceptable, as their values for L is stray, instead of the required 2. Thus we need just one factor of x plus minus to carry the correct m values, with an additional factor of x stray, which does not contribute to m, to make up the correct L. So much for the constraints from L and m. Now let's check if this satisfies the Laplace equation. Indeed it does, since the product of x plus minus and x stray is actually linear in coordinates and must be 0 under second derivatives. So the case of m equals plus minus 1 is solved. Now for m equals 0, this will be the most difficult case so far, but still quite easy. Two possible terms are allowed in this polynomial. 1x plus with x minus. The values of m cancels between them, while both adds up to the power of L equals 2. The second possibility is just two factors of x stray, which doesn't contribute to m. A and b are constant coefficients that are not yet determined. They are fixed by the Laplace equation and the normalization condition. Applying the Laplace equation. By absorbing the r square, we lose the hats. The product of x plus and x minus is just. This simple second derivative just gives So we have b in terms of a. A itself is fixed by the normalization condition. Plugging in the values of x hats, we have: if we express sine square as 1 minus cosine square, we end up with the following. And the case of m equals 0 is solved. We could in fact use this simple algorithm to solve for all the spherical harmonics by including all the terms allowed by the constraints set by L and M, then apply the Laplace equation to solve for the unknown coefficients. This is the last example on solving for spherical harmonics using the Laplace equation. Next, we shall take a closer look at the associated Legendre functions.